Today I want to present some research that we've done, published last year, in fall of last year, looking at PFAS in cosmetics and personal care products, and putting our research into the context of what has also been previously published. But first, I just wanted to start with PFAS nomenclature, and there has been a challenge to define such a broad contaminant class. For the past decade, what has counted as a PFAS has largely been coined by 𝗣𝗿𝗁 et al. In 2011, where any substance that contains at least one perfluorinated methyl group, or a CF3 group, is a PFAS. And I've included two examples here. And so according to EPA's PFAS chemical master list, there is over 12,000 PFAS that are either being regulated or are on market or have been found environmentally or biologically. It's this perfluoromoiety that imparts chemical and thermostability, hydro and lipophobicity, making PFAS useful in many different kinds of applications. In 2021, the OECD redefined what it is to be a PFAS, saying that any substance having simply a CF2 group can now be counted as a PFAS. And doing a quick PubChem search using this functional group yielded well over 1 million compounds that could be considered a PFAS. Again, here's one example here. So the structures that are depicted on this slide are those fluorine-containing chemicals that are used in various cosmetics and personal care products. For completeness, I have included two compounds that are not PFAS. It's because it seems like many compounds are. That this is an inorganic fluorinated compound where the fluorine atom is not bound to carbon. And any compound that only has one fluorine would not be considered a PFAS. But everything else is, including these HCFCs, according to the OECD definition. These are ingredients that impart the product with propellancy, making them useful in various personal care products. And over here on the right, we have a various amount of fluorinated polymers as well as non-polymers, which I'll describe in more detail within a few slides. And so, as you can see, their PFAS possess widely varying diverse structures, and this therefore gives them different physical chemical properties, environmental behaviors, and transport mechanisms of toxicity, as well as toxicokinetics. And I think this is why, as a class, it's been a large challenge both to characterize and to regulate. Now, the two most studied PFAS would be considered PFOA as well as PFOS. These are two compounds that are considered persistent, bioaccumulative, have several toxic modes of action, as well as multiple exposure routes. And so as a consequence, there have been regulatory actions to eliminate production. Those that are replacing PFOS and PFOA, however, might be equally as hazardous. Now, the risk of PFAS can also be influenced by the route of exposure, which can eventually lead to tissue accumulation. Currently, diet and drinking water are considered the primary sources of exposure. However, there are high levels of PFAS that are found in consumer products like cosmetics, as well as indoor environments, including household dust. And I think this raises lots of questions, which is, I guess one of which is, how much do consumer products contribute to indoor environment levels? And I think importantly, is there any correlation between the PFAS blood levels as well as the use of PFAS containing products? So there have been a few epidemiological studies that have tried to help answer this question, where they've looked at a positive tried to tease apart positive relationships between cosmetic application and the internal levels of PFAS. So one study published in the US took serum samples from about 450 women and found that those women with higher serum levels of PFOA and PFNA were linked to women that normally wore foundation. Now, similarly, in Korea, those women that regularly applied either cosmetics or basic skincare products resulted in a higher concentration in their breast milk of the C7-PFCA as well as PFAS. Now, linked to these epidemiological studies are some basic foundational research studies that have explicitly looked at PFAS exposure through the skin, so dermal exposure to PFAS. Currently, there's only been one PFAS assessed, which is PFOA. And so the first study looking at dermal exposure to PFOA developed parameters using a rat model. And 𝗀𝗏 et al. In 2018 then extrapolated those parameters to a person and noted that a regular daily dose of PFOA, say in a foundation, being absorbed through the skin would result in a range of PFOA levels being found in the serum, up to 3.1 nanogram per kg per day. And I think this is quite telling because this is a range that's very similar, if not higher, than that found as in the diet, which is, again, currently considered one of the primary routes of PFAS exposure. Now, last year, there was a study that came out actually looking at PFOA dermal absorption in a person. And this person had already had, like many other people, levels of PFOA in their serum. And so instead, they use labeled PFOA. They mixed that labeled PFOA in a sunscreen and applied that sunscreen to their skin. And within a matter of days, noted significant absorption with a maximum serum level of about 130 nanograms per liter. And this level represented about 9% of the long-term PFOA level, which counted all sources of PFOA exposure in this person. What's more was that the bioavailability of PFOA through the skin was up to 2%. And while this is considerably lower than oral bioavailability, where almost all of the PFOA exposed would be absorbed from the GI tract, it still translates to a potential situation where we may have daily application of a sunscreen containing PFOA during the summer months, which would consequently result in a very high plasma concentration. So what are the data gaps? So currently transdermal absorption parameters are provided only for PFOA, yet there are several different kinds of PFAS that are present in cosmetics and personal care products. So we need to first ask questions about these other kinds of PFAS, other PFCAs, PFCA precursors, and more in order to generate knowledge for this comprehensive risk assessment when it comes to PFAS in these products. So our goal of our published study was to both identify and delineate the sources of PFAS in cosmetics and personal care products. So we had several objectives, and I'll go through them one by one. The first was to simply just record PFAS that is listed in the INCI, so International Nomenclature for Cosmetic Ingredient Dictionary and Handbook. This is a great resource. It's hard to get your hands on. It's not readily accessible, but it is the only source that provides a list of compounds used in cosmetics. I've listed a few here. Pairing the INCI names, so these are the INCI names, with the CAS name and number, and sometimes even the function of that compound in a specific product, the trade name or trade name mixture. And when we coupled this search in the INCI dictionary and handbook with additional information from CAS SciFinder, PubChem, different company publications, we could generate whether or not an INCI compound was also considered a PFAS. The next was a pretty simple step. That was simply to input each ingredient into a website called INCI Decoder in order to get a list of products that contained the ingredients. So for example, one of the INCI compounds was the C9 to 15-fluoroalkyl phosphate. We did a quick search on this website and got a suite of different products containing this specific ingredient. And just to highlight here, there's a real diversity of compounds containing this ingredient, ranging from powders to different serums, sunscreen, personal care products. So we compiled in total 27 different ingredients from this INCI dictionary, and then through this website found different products that were available to purchase on the Canadian market, 38 in total, from Sephora, Walmart, different drugstores, as well as Amazon.ca. The third objective was to analyze for PFAS, like PFOA and PFOS, as well as other primary PFAS, using targeted LC-MS. But prior to analysis, we first decided to categorize these INCI ingredients in order to generate any potential hypothesis. And so the ingredients could be split between non-polymers and polymers, and this was loosely based off of characterization given by the Robert Buck paper in 2011. Now, within the non-polymers, there were also several different subcategories. So we had several different N2-based compounds. I might interchangeably use N2 with fluorotelmer. And I guess for those of you who don't know, a fluorotelmer-based compound or an N2 compound simply has an N number of fluorinated carbons. So in this case, 1, and 2 non-fluorinated carbons, or an ethylene bridge that's coupled to some sort of functional head group. So this would be a 1,2 silicon-based polyfluoroalkyl substance. We also had fluorotelmer polyfluoroalkyl phosphates, or PAPs. There were perfluorocarbons as well as polyfluoroalkyl ethers. We had a number of different polymeric substances, including fluorotelmer side chain polymers, the fluoropolymers like PTFE, as well as perfluoropolyethers. So organizing the ingredients this way generated a hypothesis where products with an N2 fluorotelmer-based ingredients would have highest levels of total PFCAs and PFCA precursors, either through the degradation of the primary ingredient, an impurity in the formulation process, or potentially even as a compound, through use as a compound or processing aid to synthesize that final ingredient. And I'll describe this in more detail later. So that the targeted analysis took place both in my lab at Carleton University, as well as our collaborators' lab at University of Montreal. And at Carleton, we looked at several PFCAs of varying chain length. We looked at PFCA precursors like the PAPs, shown here. We also looked at a few PFSAs, including PFOS, the C8, as well as PFSA precursors, and a couple of different PFAS as well. The extraction really followed typical extraction procedures that have been published by many different groups. This is where we took about 100 milligrams of the product, sonicated in basic methanol, and then cleaned up the matrix using activated carbon. We then analyzed every sample using electrospray negative ionization, tandem mass spectrometry. We used labeled internal standards. And we coupled all of the analysis of samples with QA/QCs, method blanks, spike and recoveries, matrix effects, and as well as replicates. The importance of labeled standards really came into play because we noted enhanced matrix for many of our analytes. Adding in a labeled internal standard helped bring those recoveries down into an acceptable recovery range. Now, a subset of samples was also sent to Sébastien Solvay's lab at University of Montreal for additional analysis using their 𝘀𝗰𝗶𝗃 trap. They had additional targeted analytes, including some PFCA precursors, the FTCAs and the FTUCAs, as well as emerging PFAS that seem to be predominating in again, many different published studies from the past several years. They had a method that looked for well over 200 different PFAS using suspect screening. I did not have the space to list all 200, except if it was in really tiny font. So instead, I just included all of the PFAS that were detected in any of our cosmetic and personal care products. So like our lab, they also had a rigorous QA/QC protocol. They analyzed different laboratory blanks in parallel to the samples that we sent them and noted blank levels that contained PFCAs as well as PFSAs, but levels that were much lower than those that were found in our product extracts and were simply subtracted out. Now, looking at the results, so we observed PFAS in the 17 cosmetics and 21 personal care products. The PFCA concentrations were much higher than any and all of the PFSAs, with concentrations up to 29 microgram per gram. Dominating the PFCA signature was the C6 PFCA, with this 25 nanogram per gram as a median concentration. In comparison, the highest PFSA concentration was about 5 times lower, corresponding to the C4 PFSA. But really dominating the levels of our targeted analysis were the concentrations of PAPs, with levels as high as 14.5 milligram per gram. So the compounds the products that contain the highest level of these PAPs were unsurprisingly those products that contain PAPs as an actual ingredient. So cosmetic 1 to 4 all had PAPs, some form of PAPs as an ingredient. So cosmetic 1 was a bronzer that contained the C9 to 15 fluoroalkyl phosphates, which is a mixture of monoPAPs, where we had 1 fluorinated chain. Cosmetic 2 to 4 were foundations that contained a mix of both monoPAPs as well as diPAPs with 2 fluorinated chains of varying chain lengths as well. Now, PFAS ingredients did not always align. In this case, it did, with high extracted PFAS levels. So, for example, we also found that PFCA precursors like the FTCAs and the FTUCAs at high levels in several different cosmetics and personal care products. So this was a surprise because these are compounds that are not industrially produced for any application. And so along the same lines, they should not be present within these cosmetics. They're not considered ingredients. And so this leads back to the original hypothesis. So in this case, the N2 polyfluoroalkyl phosphates have been known to biologically and enzymatically and microbially transform in active environments by hydrolysis to the 6,2-epto, which can subsequently undergo oxidation to the intermediates, the fluorotelomere carboxylic acid, as well as fluorotelomere unsaturated carboxylic acid, which then further undergo oxidation to the C6 PFCA, as well as minor amounts of the C5 as well as the C7. So our original hypothesis was that products containing this fluorotelomere-based ingredient, like these PAPs, would have highest levels of PFCAs and their precursors, even though these compounds are not specific ingredients. Instead, and rather, they'd be present either as biotransformation products through this process, or in the case of PFCAs, it's more complicated. The presence of PFCAs could also be present as impurities through the formulation process or through their use as a base to synthesize a final cosmetic ingredient. And so to tease apart these different potential sources, we performed a Spearman correlation analysis using these PAPs, comparing the presence of the PAPs, the levels of the PAPs, to the levels of the PAPs intermediate compounds, as well as the PFCA terminal products. And for the 6,2 PAPs, the mono and the di PAPs, they had the levels were significantly correlated to the presence of their intermediates and their respective PFCAs. And so this suggests that the PAPs somewhere along the way of the final product being purchased, there is possible degradation or biotransformation during either the formulation or the end product use. So in addition to the PAPs, there were a few other ingredient classes that also had a fluorotelomere-based moiety. This is the result that showed the total PFCAs in all of the ingredient classes. And you can note that for both short chain and long chain PFCA levels, there is a high amount of I guess, a wide range of PFCA concentrations in all product classes, which left our hypothesis fairly unsupported. But when we looked at the individual PFCA congener levels, there were a few interesting trends that appeared. So products that contain this N2 silicon-based polyfluoroalkyl substance, particularly, moving to the graph over here, these perfluorooctyl triethoxysilanes, were coupled to high levels of the short chain PFCAs, particularly the C6. And so we rationalized that this was due to the presence of the 6,2 fluorotelomere moiety within this ingredient. Now, along the same lines, products that contain perfluorobutyl ethers had high levels of the PFBA, the C4 PFCA. Now, these ethers do not contain any fluorotelomere-based moiety, but instead have a perfluorobutyl moiety. So it's reasonable to think that the PFBA may be forming from its degradation or through a formulation impurity. Now, another surprising result was that we noted a wide range of targeted PFCAs in products that did not explicitly list PFAS as an ingredient, with median levels of 88 and 34 nanogram per gram for the short and long chain PFCAs. So this would have been a very surprising result had it not been for a study that was published in 2021 by Heather Whiteley and 𝗀𝗄𝗄𝗂𝗂𝗂𝗂𝗂𝗂𝗂𝗂𝗂 group that noted a similar finding. So within their published study, they noted that only 8% of cosmetics that were screened for their total fluorine actually listed PFAS as ingredients. And so in this study, they tried to delineate possible sources of PFAS exposure. So they rationalized that PFAS could either be present in the product as intentional additives or as unintentional contaminants. And generated this heat map trying to connect the various ingredients, the non-fluorinated, non-PFAS ingredients that had high or low levels of total fluorine. And coming out of this research, they noted that ingredients can sometimes be co-treated with a PFAS like PAPs in order to impart and improve the ingredient's durability as well as wear. And so ingredients like mica, silica, talc, various different colorants shown here, have the potential for being treated with different PFAS, which would not be included on the final ingredient list because they do not serve as a final ingredient like, say, mica or talc would. And furthermore, ingredients like dimethicone and methicone also have a fluorinated alternative. And so there's potential there for the product maybe to list the generic name rather than explicitly state whether it's fluorinated or unfluorinated, although really this has yet to be rigorously assessed. So PFAS obviously can be an unintentional contaminants. PFAS contamination comes from a lot of different sources. And so it's known that equipment can be contaminated with PFAS. PFAS can come from potentially its presence in other ingredients like water, as well as the use of fluorinated storage containers. But again, these are all open-ended questions that have really yet to be answered with rigorous research protocols. So the last objective of the study was to screen for over 200 PFAS using suspect screening techniques and high-resolution mass spectrometry. This last objective was prompted by data gaps that have emerged from previous research. So the study from 𝗀𝗏 et al. Measured both targeted PFAS along with total fluorine, shown by these yellow bars, as well as total extractable organic fluorine using a technique called combustion ion chromatography. And I just want to draw your attention to the subset in this figure. And so this is a figure inlay that shows the results from 3 different foundations, all of which contains PAPs as an active ingredient. These foundations had the highest level of targeted PFAS, but they also had high levels of total fluorine, which indicated the presence of non-extractable substances like inorganic fluorine or polymers. And I think most interestingly from this inlay, there was a large percentage of extractable organic fluorine, which hints at the presence of other fluorinated substances that have not been included in the target analysis. So we aim to fill this gap using suspect screening. So we send a subset of samples for this to apply this screening method. So here is the first result. This is cosmetic 1, which is again a bronzer that listed 1 PFAS ingredient, the mixture of monopaps. And what we found was 40 distinct PFAS, the PFCAs, the FTCAs, PAPs, but also lots of unexpected PFAS, given that they are completely unrelated to the active ingredient. So all products were analyzed. This is a graph that has all of the targeted analytes removed. And so these are compounds that are again, completely unrelated to any sort of active PFAS ingredient. So what we noted was that in cosmetic 1, there were levels of perfluorophosphinic acids detected. These are typically known as wetting agents and have been previously measured in matrices like wastewater, human serum, indoor dust. So another question, is cosmetics a potential source of this contamination, of this environmental and indoor contamination? Another interesting result here is that we also detected several monohydrogen substituted PFCA compounds in many different product extracts. These are an emerging PFAS class, considered one of the replacement options for PFCAs like PFOA. We also noted in one shave product here the presence of this PFAS, which is known to be a degradation product of sulfoamidoethanols. Cyclic PFCAs were observed again in cosmetic 1, as well as fluorotelomere sulfonates, these two here. And finally, we noted the presence of 3 FFF related PFAS here and here, observed in several products, including those cosmetic 17, which were supposedly PFAS free. So we then, and this wasn't part of the published study, but afterwards we decided to do a loose comparison to cosmetic 1 and the results found from cosmetics 1 to the analysis that was published by the paper by 𝗀𝗲𝗍 et al. So using the analytes in the red square, comparing the percentage of analytes within our targeted analysis, the PAPs and PFCAs, which are also included in the targeted analysis from the 𝗀𝗲𝗍 paper. Our targeted analytes comprise about 80% of the PFAS found within cosmetic 1. The suspect screening analytes comprised about 20%. Now, this is, I think, a large fraction was filled by our suspect screening, but it's still not capturing all of the extractable organic fluorine that potentially might be in there. So I think that previous result suggests that there should be additional targeted analysis and high resolution mass spectrometry applied to these products. There's still a need for it in order to fill missing mass balances, which includes, of course, quantifying for the actual ingredients. We've quantified for PAPs, but as you can see, there's lots of other non-polymeric PFAS that could be quantified as well. So in addition to quantifying for the actual ingredients, the mass balance may be filled by also measuring for the C2 PFCA, trifluoroacetic acid, or TFA, since some of these ingredients contained 1,2-fluorotelomere-based moiety, which then may be susceptible to degradation to form the C2 for PFCA. We also didn't include the quantitation of any isomers, like the isobutyl PFBA. And in addition, we did not include any semi-volatile or neutral PFAS in our measurements, like these methacrylates, which have been confirmed by previous work, the work by Heather Whitehead, to be impurities in some of the products that they tested. So just to start summarizing the cosmetic and personal care product work, and again, identify gaps that should be filled. We know that PFAS migration and contamination in both biological samples as well as the environment is complicated given the many different sources and pathways of exposure. In response to regulatory and research activities, manufacturers are substituting common PFAS like PFOS and PFOA with alternative PFAS like these HPFCAs and short chain PFAS having C4 and C6 linkages. And yet these alternatives are already being detected in both biotic and abiotic environments. We know that these short-chain PFAS can accumulate in plants and agricultural crops. They are still considered environmentally persistent because they still possess those carbon-fluorine unbreakable bonds. And they have the potential, therefore, for mobility as well as long-range transport. Now, questions stemming from this work and others is the potential for cosmetics and personal care products as a potential exposure source to these different matrices and environments. Now, just quickly, with respect to current regulations, in Canada, the federal regulations prohibit any products that contain PFOA, long-chain PFCAs, PFAS, and the umbrella of precursors. So we found long-chain PFCAs and their precursors, some of which are ingredients in cosmetics, indicating that these products are an abrogation of these regulations. Now, furthermore, there is a Canadian cosmetic hot list that contains all the ingredients prohibited from use of cosmetics and personal care products in Canada. However, PFAS are not yet listed on that hot list. There are some suppliers like Sephora, which now, I think as of 2021, include PFAS on their clean lists when you purchase a clean cosmetic or personal care product. Now, in the US, I think there's been more action within this field. So there's been a few pieces of legislation, potential regulations, like the new PFAS and Cosmetic Act introduced to Senate in 2021, as well as the Agency for Toxic Substances and Disease Registry has acted to reduce exposure to PFAS through different consumer goods like cosmetics. And some states like California are now are banning intentionally added PFAS to these products. So I think just 3 take-home messages from this talk. We found specific INCI ingredients to be linked with high levels of targeted PFAS. These first 2 ingredients are linked to the PAPs because they are the PAPs. This ingredient, the silane, is linked to levels of PFHXA, and any perfluorobutyl ether was linked in our study to the PFBA, the C4-PFCA. And as we know, many products associated with short-chain PFAS may then be contributing to the environmental load of these PFAS. We also found diverse PFAS present as cosmetics in these products, regardless of whether they were actually associated with a PFAS-related ingredient. So I think the next steps from this is that we should put emphasis on determining the sources of PFAS contamination in order to both reduce these PFAS as well as to generate appropriate risk management techniques. And then final message is that transdermal exposure is not insignificant. The fact that PFOA, and potentially even more so from non-ionized PFAS, lead to high internal levels with continuous use of PFAS-containing cosmetics and personal care products is something that should not, of course, be ignored. And with that, I appreciate you listening to this talk and seminar. It was Keegan Harris, a master's student, that generated most of the work that came out of our lab.